7, Exponents and Exponential Functions. So in this video, we will start talking about learning target 7a, which is all about the properties of exponents. By the end of this lesson, you will be able to apply the properties for zero and negative exponents, as well as apply the property of multiplication of powers with the same base to simplify exponential expressions, and then apply properties of raising exponents to powers to simplify expressions, as well as apply the property of division of powers with the same base to simplify expressions. Let's start with a little review from a prior unit. So remember, a power, a power has two parts, a base and an exponent. The exponent tells us the number of times to use the base as a factor. So in this example down here, 2 is our base and 3 is our exponent. So this tells us that that exponent of 3 says I will use my base of 2 and multiply it to itself 3 times, which is how we get 2 times 2 times 2. So I have 3 of the 2's all being multiplied. There's a couple ways we could read this. We could read this as 2 cubed, or we could read this as 2 to the third power. And for some exponents, we will have kind of a shorthand like the 2 cubed, or if we had a 2 as our exponent, that would be considered squared. But for anything that is the fourth exponent or higher, we will say that that is the fourth power, fifth power, and etc. Okay, let's just practice expanding the expression. So in this first example right here, it is pronounced y cubed, or y to the third, and this would be equal to y times y times y. So I have 3 y's because my exponent is a 3. In example B, this says a to the fifth, and that tells me that I'm going to multiply a to itself 5 times, since my exponent is a 5 this time. So I'll get a times a times a times a times a. And as you can see, it's a lot more cumbersome to expand out the expression, which is why we have the shorthand for exponent, so that we can condense it down our expressions as much as possible. But it's important to understand, well, what do those exponents really mean, and how can they help us in other problems? Okay. There are 7 properties of exponents. We're going to talk about these first 2. The first one is 0 as an exponent. And what that means is that if a is any non-zero number, then a to the 0 power equals 1. We'll talk about y in a second, but any non-zero number to a 0 power is going to be equal to 1, which might sound a little strange, but we'll talk about why. The second property of exponents is, what do I do when I have negative exponents? So if a is any non-zero number and n is a rational number, then if I have a to the negative n, so my exponent here is negative, then I could rewrite this as 1 over a to the positive n, so that I have only positive exponents on the right-hand side. And let's really talk about why. So let's go through this chain that we have here. So 2 to the fourth would be the same thing as 2 times 2 times 2 times 2, which would give us 16. 2 to the third would be 2 times 2 times 2, which is going to be 8. 2 squared would be 2 times 2, which would give us 4. And then 2 to the first is just 2, and that's all, because I have a first exponent, so I only want one of those bases. We know these from working with exponents before. Let's look at if there's any connections between those two. So do you notice anything between these numbers when you look at 16, 8, 4, and 2? What I notice is that if I'm going up the chain, so to get from 2 to 4, I multiplied by 2. To get from 4 to 8, I multiplied by 2. And to get from 8 to 16, I had to multiply by 2. And that should hopefully make a connection with those exponents, because each of these, as we go up, is adding one more multiplication by 2 because the exponent is getting higher by one integer value. But on the other end, if I think about how I'm moving down this chain, to get from 16 to 8, what I had to do was I divided by 2. Again, to get from 8 to 4, I also divided by 2. And to get from 4 to 2, I divided by 2 again. So, although we're not exactly sure what 2 to the 0 power is, this pattern should continue because exponents have a relation and have a connection together. So if this division by 2 works for the first three, and it would work for any powers 2 to the 5th and higher as well, it should work again. So what that means is if I divide by 2, 2 divided by 2 would give me 1. Well, if I look here, anything to the 0 power is going to be equal to 1. That was our rule up here. And this is one example how we can see why that is true. Now let's continue this pattern. So if I divide by 2 again, then 1 divided by 2 would give me 1/2. But think about this. This exponent here was a negative first. Technically right here I do have an invisible 2 to the first power. So this is so far backing up this second, I'm going to highlight it in green, this second rule of negative exponents, where if I have a to the negative n, that's equal to 1 over a to the n. But let's not take it at face value yet. Let's make sure that's really true. So I'm going to continue this pattern again and divide by 2 and see what we get. I'm running out of space down there, so I'm going to write it off to the side. So I'm starting with 1/2 and I'm going to divide by 2. Well, technically I'm dividing by 2 over 1. And if I have a fraction divided by a fraction, that's the same as multiplying by the reciprocal of the denominator. You might have heard it in another class as keep, change, flip. So I would keep the numerator, so I'd keep the 1/2 the same. I would change the division to be multiplication, and I would flip the denominator to be 1 over 2. So when I have a fraction divided by a fraction, that's the same thing as multiplying by what we call the reciprocal or the flip of the denominator. Or you can think about it as keep, change the sign, and flip the denominator. When I do that, well, I multiply fractions by multiplying directly across. So 1 times 1 is 1, and then 2 times 2 would give me 4. So over here, I'm going to try to fit it in, that would mean that 2 to the negative second should equal 1 over 4. But I have to somehow relate that back to this rule and think about, well, does that rule really work? Well, think about this. We could rewrite the number 4 as 2 squared. We had done this a little bit earlier when we calculated what 2 squared was as 4. So really, what I have down here is 1 over 2 to the second. So I started with 2 to the negative 2, and when I simplified it using our division by 2 on each one of these to see our pattern, that is the same thing as rewriting it as 1 over 2 squared. And hopefully through these examples, we're kind of starting to see how that pattern arises and why these two first rules are what they are. So we're going to see 7 different properties of exponents, and I don't want you guys to just take them at face value. You should really understand why they're true, because then it's less about memorizing a fact and more about understanding what's happening with all of these different types of exponents. Let's do one more just to double check our pattern here. So we would have to divide by 2 again. So now I'm dividing 1/4 by 2. So I'll get 1/4 divided by 2. What would we get if we simplified that down? Why don't you guys pause the video and simplify that on your own first. Again, when I have division by 2, I'm really dividing by 2 over 1. So if I have a fraction divided by something else, I've got to multiply by the reciprocal of the denominator. So I'll get 1/4 times 1/2, multiply directly across, and we'll end up with 1 over 8, which, if I think about it, we've seen 8 before. 8 is 2 to the 3rd power, so this is equivalent to 1 over 2 to the 3rd. So this is holding up our pattern of when I have a negative exponent, so this 2 to the negative 3rd, that is equal to 1 over 2 to the positive 3rd. And we can continue this pattern on for more, either higher exponents and go 2 to the 5th and higher. We could also do this for 2 to the negative 4th and smaller exponent numbers. And we could also do this with a different base. So this does not just hold true if it's base 2. I could do this with base 3, base 4, 5, 6, 7, etc. I can do this for any base where my base, is a non-zero number. Okay. So those are our first two properties of exponents. Anything to the 0 power equals 1. So no matter how complicated I make the base, whatever it is, if it's to the 0 power, it's going to be equal to 1. And then if I have any base to a negative exponent, I can rewrite this as 1 over a to the positive n then. To kind of go along with this second property, I want you guys to think about what would happen if I had a negative exponent in the denominator to begin with. So if I started with something that was 1 over a to the negative n, I would have to think about, well, how can I fix that and write it as a positive exponent? Well, we know already that a to the negative n, I can rewrite that as 1 over a to the n by using our negative exponent property. Then from here, this is going to be one of those divisions of a fraction, so I'm going to multiply by the reciprocal of the denominator. So the 1 in the numerator will stay. I'm going to multiply by a to the n over 1, which simplifies down to just be a to the n, since multiplying and dividing by 1 will not change anything. So on the kind of flip side, if I have a negative exponent in the denominator, I can make it a positive exponent by moving it to the numerator. Let's look at some examples with these two properties of exponents first, and then we'll start to add in other properties. So our first example says 5.14 all to the 0 power. Well, no matter how complicated I make that base here, so my base is 5.14, if my exponent is a 0, this will always be equal to 1 then. Same thing with b. Even if I have a negative number, do notice the fact that I do have parentheses around this, so if there weren't parentheses, this would be different, but because the whole negative 3 is inside the parentheses being raised to the 0 power, that's going to be equal to 1. Okay, let's look at c. So c says x times y to the 0 power. So I don't just have to have my base being a number, and we're going to see in this learning target that most of the time our base is actually going to be other variables, but these properties still hold. So whatever's inside here, my x times y, it's all being raised to the 0 power, so this entire expression is equal to 1. Okay, let's look at example D. It says 5 to the negative second. So now we're going back to that negative exponent. We know by definition that if I want to write this without any negative exponents, since that's what the problem said, it said simplify the following without any negative exponents, the first thing I have to do is get rid of that negative exponent. And I can do that by rewriting this as 1 over 5 to the positive 2. Because when we flip that exponent down to the denominator, it's going to become positive. We can keep simplifying this because 5 squared we know is 25, so our final answer will give us 1 over 25. Okay, let's look at a couple more together. So why don't you guys pause the video and do example E on your own first right now, and then we'll check it together. Okay, let's check example E. So E says negative 3 all to the negative second power. So the entire negative 3 is inside those parentheses, which means when I flip this to make it a positive exponent, the entire negative 3 will move down to the denominator, and that will become a positive 2, and we'll get 1 over negative 3 to the second. We can go ahead and keep simplifying that, and we know that negative 3 to the second would equal positive 9, since we have a negative 3 times a negative 3, so we would get a positive 9. I'm going to have us keep going down the left-hand side of this, and then we'll come back to part J. So let's look at F. Why don't you guys pause the video and do F on your own first, and then we'll check it together. Okay, as we check f, notice what it says -3 all to the -3rd exponent. So that would be equal to 1 over -3 all to the +3 exponent. Now I gotta be careful. -3 cubed would be -3 times -3 times a -3. So if I multiply 3 negatives, I am going to end up with a negative answer, and I'd have -1 over 27. Since 3 times 3 times 3 would give us 27, and then the negative is coming because I have 3 negative signs here. So just be careful with your negative signs when you're raising them to powers. Okay, let's look at example G. So example G says x to the -7th. So I need to simplify without negative exponents, so I'm going to go ahead and flip this and rewrite it as 1 over x to the +7. Now from here, in the prior problems, we continued to simplify because I had a base that was a number. So I knew what -3 squared was, we knew what -3 cubed was, but I don't know what x is here, so x to the 7th is just going to stay as x to the 7th, and we're actually done then. Okay, let's look at example H. So example H is kind of incorporating multiple properties here. So we have 32 to the 0 power, and then we have 4 to the -2nd power. Well, let's take this one step at a time. So we know that anything to the 0 power is equal to what number? It's going to be equal to 1. So 32 to the 0 power is going to be equal to 1. So I can replace 32 to the 0 with 1. I'm going to just rewrite the 4 to the -2. Now we know that 1 times anything isn't going to change it. So my next step is to think about how can I rewrite 4 to the -2nd. I could do that by flipping that 4 to the denominator, and it would become 1 over 4 to the +2, which we could then simplify, and 4 squared is 16. So we would get 1 over 16. There we go. Okay, let's look at example I. So in example I, it says 5 times a to the 3rd times b to the -2. So our goal, remember, is to simplify without any negative exponents, which means I would have to combine any like terms that I could and just get rid of any negative exponents. So the 5 and the a to the cube, those guys are good. There's no negative exponents here, so I can go ahead and just rewrite 5a to the 3rd. There's nothing that I could change there, and there's nothing that I need to change. But this b to the -2, I will have to rewrite. So b to the -2nd can be rewritten as 1 over b to the +2. This is actually going to be our final answer, but I want us to start writing these as one whole fraction anytime we end up getting a fraction. So I'm going to have 5a to the 3rd in the numerator, technically times 1, over b to the 2nd. And let's just get used to writing it as one entire fraction together. There's nothing else I can simplify because I have a base which is a and a base which is b, and because they're different bases, there's no way to simplify those together. Okay, let's look at example J. Why don't you guys pause the video and try example J, because we've talked about something similar, and then we'll check it together. Okay, let's check example J. So the first thing I notice is that negative exponent that we have. So we're going to want to go ahead and rewrite this then. I still have 1 over. X to the -5th can be rewritten as 1 over x to the +5th. From here, we have gotten rid of all the negative exponents, but this is really, really messy. So we want to rewrite this so that we just have one fraction instead of number divided by a fraction. So the way we would do that is multiply by the reciprocal of the denominator. So keep the numerator, change division to multiplication, and then flip the denominator. Then 1 times x to the 5th over 1 is just going to be x to the +5. There we go. Okay, why don't you guys pause the video and try k on your own as well. Okay, let's check example k. So we've got quite a few pieces going on here. We have 4 times c to the -3rd times b times a to the 0. So the 4 is good. that's our coefficient. I can't do anything with that. There's nothing to combine it to. But c to the negative third, I could rewrite as 1 over c to the positive third. b is good. It's b to the first power technically, so I'm good there. And then a to the 0, remember anything to the 0 power is 1, so I get times 1. Let's just kind of clean this up and write it as one whole fraction. So we would get 4 times b in the numerator, and then c to the third in our denominator. And that will be our final answer. Okay, let's look at L and M. So L and M look really similar to each other. I have a 3 times x to the negative 2 in L, and then in example M, we have 3x all raised to the negative 2. So what do you guys think? Do you think that since these look pretty similar, they'll give us the same answer, or are these going to be two different types of problems? So these are going to be two very different types of problems because of those parentheses. So those parentheses in part M versus not having parentheses in part L is going to make a huge difference. So in part L, because there's no parentheses here, that means that only the x is raised to the negative second power. Versus in part M, which we'll do in a second, the entire 3x is being raised to the negative second power. So let's tackle question L first. So the 3 can never change because it doesn't have any negative 2 exponent on it, but we can rewrite x to the negative 2 as 1 over x to the positive 2, and then from here I can write it as one whole fraction to make it 3 over x squared. Now in example M, this is going to be different because the entire 3x is being raised to the negative second, so I'm going to flip the whole thing to the denominator and write this as 1 over 3x. Notice I still need those parentheses, now to the positive 2. Now from here, I need to simplify this further, and we can distribute the squared power here. So we get 1 over 3 squared times our x squared, since both the 3 and the x are being raised to the second power. From here, we can simplify the 3 squared as 9, and we get 1 over 9x to the second. So as we can see, the answers that we got for L and M are very different because in L, the 3 is not affected by the exponent, versus in part M, that 3 is inside the exponent, so I need to distribute that negative 2 exponent and simplify from there. Okay, our last example of this type. It says a to the negative 5th over b to the second. Why don't you guys pause the video and try example N on your own first, and then we'll check it together. Okay, let's check example N. So the b to the second is good. That guy's okay in the denominator, so I'm going to just start by breaking this apart into two things that are being multiplied. So I have the a to the negative 5th, that's technically over 1 because it's in the numerator, then times 1 over b squared. The 1 over b squared is good to go. There's no negative exponents, so that guy's already simplified. But the a to the negative 5th, we can simplify and write as 1 over a to the positive 5. We still have times 1 over b squared. Then just to write it as one condensed answer together, we'll write it as 1 over a to the 5th times b to the second. One thing I do want to point out is you guys can see that I'm writing quite a few steps as I go through these. Now as you get better with these, you might be doing some of those steps in your head, which is okay, to go straight to our final answer on like example K or example N, for instance. But anytime you have coefficients on here, so with the negative 3's that we had here, the 4, the 5, the 3 versus the 3 inside the parentheses, you really want to be careful and take the time to write out those steps so that you make sure that you're not making any silly errors as you go through them. Okay, let's look at our next property. So our next property says multiplying powers with the same base. So we've already done the 0 as an exponent and how to deal with negative exponents. So this next property is about what happens if I multiply two bases that are the same. How do I deal with their exponents to combine them? Well, if I have a to the m times a to the n, that's going to be equal to a to the m plus n. So if, I have it written out down here for us, if we multiply powers with the same base, then we add the exponents together. And let's really talk about why, because as I said at the beginning, you don't want to just have these rules and try to memorize them. You want to understand why this stuff is true so that you can see the larger picture of what's going on, not only for this class, but as you take other math classes. So let's talk about why by using this example. So we have 3 to the 4th times 3 to the 2nd. I'm going to expand out what this means. So 3 to the 4th would mean 3 times 3 times 3 times 3. So I've got 4 of them here, so 4 times. And then 3 to the 2nd would mean 3 times 3. Oops, sorry, that got a little messy, so I have 2 times there. Well, technically these big parentheses that I put around them don't matter because multiplication is commutative, so I really have 3 times 3 times 3 times 3 times 3 times 3. So total, I really have 6 of them. Now if I look back at my two exponents of 4 and 2, I can get to 6 by adding them. So that's why we end up adding our exponents, because this is the same thing as doing 3 to the 4 plus 2, which would give me 3 to the 6. And I know that I should end up with 6 of them because when I expanded it out, I had 6 3s overall, which we got by technically adding the 4 and the 2 as my exponents. Okay, let's do some of these examples together. So let's start with example 2. Example 3a. It says 2 to the 4th times 2 to the 3rd. Again, our goal is to simplify without any negative exponents. So if we look at this guy, I have the same base here. So that's the first thing we always have to check. If I go back up to this rule, this only works because both of these bases are a's, and the base, you'll notice, does not change. All I end up doing is adding the exponents when the bases are the same, and I'm multiplying them. So in part A, the bases are the same. That's the first thing I gotta check. So I have a 2 and a 2 as my base. So I can add the exponents, and I'll get 2 to the 4 plus 3, which we can simplify as 2 to the 7th. Then from here, I gotta figure out what 2 to the 7th is. Off the top of my head, I know that 2 to the 5th is 32. So I need to multiply by 2 more times. So 32 times 2 would give me 64, and then 64 times 2 would give me 128. So 2 to the 7th is equal to 128. Okay, let's look at example B. Why don't you guys pause the video and try B on your own first, and then we'll check it together. Okay, let's check example B. So we have 4 to the negative 2 times 4 to the 5th. So the first thing I have to think about is, are my bases the same? And they are. I have a 4 and a 4. So because they're the same, I can add the exponents. So I'll get 4 and then raised to the negative 2 plus 5. So even though this exponent is negative, I can still add them together. Just make sure you include that negative. Negative 2 plus 5 will give me 3. So I'll end up with 4 to the 3rd, which would be 4 times 4 times 4, which would give me 64. Okay. Example C. Example C looks similar, but now we're dealing with more variables. So I have z to the 5th times 9 z to the negative 12th. So this 9 is a coefficient on the second z term, but because multiplication is commutative, I could rewrite this as 9 and then the z to the 5th and a z to the negative 12th. So I can kind of move that coefficient in front, which we tend to do just so that in case we have multiple coefficients, we'll end up combining them together. And we'll see that in an example in a little bit. From here, what's the first thing you should be asking yourself? You should be thinking about, do I have the same base? So in this case, I do have the same base. They're both z. So I can add those exponents and I would get 9z to the 5 plus, negative 12. I can then add those together and I'll get 9z to the negative 7th, which, hopefully we're remembering, I have to deal with my negative exponents. So to simplify our negative exponents, I would have to flip this. I'm going to rewrite this to give myself a little bit more space. So I'm going to write our 9z to the negative 7th over here. Now I have to rewrite this z to the negative 7th. Now notice we had those two examples on the prior page where the difference between when the coefficient is inside the parentheses or when there are no parentheses, so it's outside. In this case, that 9 is not being raised to the negative 7, so the 9 is never going to change then because it's not being raised to the negative 7th. But I can flip the z over and make it 1 over z to the 7th. And then because we want to write this as one fraction, I'll have 9 on top over z to the 7th in the denominator. And that will be our final answer for part C. Okay, let's look at part D. So we have a lot of moving pieces now. 5 times x to the 4th times x to the 9th times 3x. So if you notice in this one, I have two coefficients. I have 5, I have 3. I also technically have an invisible 1 in front of the x to the 9th. So I'm going to regroup these and I'm going to pull the 5 and the 3 in the beginning. They're being multiplied because everything is being multiplied in this problem. And then I'm going to just rewrite the x to the 4th, x to the 9th, and the single x. Yeah? Let's erase that arrow sign so we're not getting confused. From here, let's go ahead and simplify. So 5 times 3 I can multiply, and we know that's equal to 15. And then for my exponents, because I have the same base, they're all x's, I can go ahead and add those together. And I get x to the 4 plus 9 plus 1. Don't forget that that's an invisible 1 there is my exponent. Sorry, that plus sign makes it look like two 4s. So 4 plus, oh my, about 4 plus 9. So when I add those together, remember we already have our 15, and then I end up with x to the 14th power. And there is our final answer. Okay, I want you guys to pause the video and try example E on your own first, and then we'll check it together. Okay, let's check example E. So I have negative a times 9b to the 4th times 3a to the 2nd. So let's notice I've got a negative 1 as a coefficient, a 9, and a 3. So the first thing I'm going to do is move those all in front. So I have a negative 1 times a 9 times a 3, which we'll simplify in a second. Then I have an a b to the 4th, and an a squared. Will I be able to add all of those exponents together? What do you guys think? In this case, I won't be able to because I have two different bases. I have the a base, so I have the a and the a squared, and then we have this b to the 4th. I cannot combine the b to the 4th with the a's. So I'm going to regroup them so that the a's are next to each other. So I have a times a squared, and then times the b to the 4th. From here, let's multiply all of our coefficients. So negative 1 times 9 times 3 would give us a negative 27. A times a squared, we can add those exponents, and I would get a to the 3rd, since I have that 1 plus 2. And then the b to the 4th doesn't have anybody that it can get combined with, since the base here is b and the base over here is a, and those are different variables, so I cannot combine this any further. So that is our answer to example E. Why don't you guys pause the video again and try example F on your own first. Okay, let's check example F. It says negative 4c to the negative 3rd times 5d to the 2nd times 2d to the 4th. So I have a couple coefficients. I have a negative 4, a 5, and a 2. You'll notice here that I didn't use the multiplication sign when I typed out the problem. I used parentheses, but those are equivalent. The parentheses, the multiplication sign, they both mean multiplication, so it's the same type of problem. If I put all those coefficients in front together, I have negative 4 times 5 times 2. Now let's look at what I have. I have a c to the negative 3rd, and then I have a d to the 2nd, so that's a different variable, so I'm going to use a different color to highlight it, and a d to the 4th. So in this case, I can't combine the c to the negative 3rd with anything, but the d to the 2nd and the d to the 4th will be able to get combined together. Let's start with the coefficients. So negative 4 times 5 times 2 would give me a negative 40. C to the negative third can't get combined with anybody, but d to the second times d to the fourth can become d to the 6th power by adding the exponents. From here, the last thing I have to do is simplify any negative exponents. So I can't combine this or condense this down anymore, but the c to the negative third I have to rewrite as a positive exponent. So that will end up being moved down to the denominator. The d to the 6th will definitely stay in the numerator since it's a positive exponent. But what do you guys think about the negative 40? Will that stay in the numerator or will it move down to the denominator? So in this case, the only way I can move something to the denominator is if it has a negative exponent. Now, 40 itself is negative, but its exponent is technically a positive 1, which means no, it will stay in the numerator. So I'll get negative 40 times d to the 6th all over c to the third. So I know it's really tempting when that coefficient is negative to want to move it to the denominator, but it all depends on the exponent. And if the exponent is positive, it stays where it is at. Okay, our last example of this type. So it says x to the a times x to the b times 3x to the c. Why don't you guys pause the video and try this guy on your own too, and then we'll check him. Okay, so let's check this. I have only one coefficient. I technically have a 1 in front of the other two, but 1 times anything is still the number, so I have 3 in front, then I have an x to the a, x to the b, and an x to the c. Well, this looks really funky because my exponents are now variables as well. But that's okay. We can treat this the same that we've done any other problem. What I'm looking at is to see if my bases are the same. Well, in each one of these, I have an x as my base, so I can combine these together, and this will become x to the a plus b plus c, which, because I don't know what a, b, and c are, I can't combine them more than that, but I can write it with one base. And we are done with that one. So in this video, we finished talking about the first 3 properties, and in our later videos, we'll talk about the